Right, recording is rolling. So welcome to Wednesday. The agenda for today is we're going to finish these ray diagrams for reflection. You guys remember yesterday we were doing all these convex parabolic mirrors, and we almost started on the concave, but that was about time covering. So we'll finish these ray diagrams. The convex yesterday, we'll do concave today. Then there's actually an equation that you can apply algebra to also tell you where an image is going to be that would align with what these ray diagrams are. So it's ray diagrams are a graphical method, but to what there's also an algebraic method to solve for where a reflection is going to be. We'll look at a full application of some concave reflecting surfaces. We're going to do those chapter 17 book questions. And we might have a couple of minutes left at the end of class where I can start telling you guys about refraction. Refraction is like a light passes through through some transparent material and actually bends. Right? That's this guy right here. So maybe last a couple of minutes class. Right, so pick up where we left off. Remember you guys yesterday we're looking at reflection, and there was this law of reflection. So I'm going to go back and just recap some main ideas that led to all this stuff, right? So law of reflection just says that the angle of reflection is equal to the angle of incidence. Now, what does that mean exactly? That means that you're measuring these angles with respect to a normal line. The normal means perpendicular, so perpendicular to some surface. Let's take a look at like this curved surface right here. Now, this one is a convex parabolic mirror, right? So it's like the shape of a parabola. I was saying that you could fit like a circle, like flush to this point right here, like a circle. Now, how big could you make that circle before it say like started separating them? Right? The biggest circle you can fit, you can see the one dashed outline here, has some radial size r, and that's where you can. I think it. Okay. Say you're following one particular ray. Now there are like a billion rays bouncing off the sky all different directions, but you only follow a couple. Is all you need to figure out where the reflection is going to be. So we're going to follow one ray parallel to this ground. It's going to boing, bounce off kind of up to the left. See, if it was a plane mirror, it would bounce straight back. You guys saw that with Paul Hewitt and his candle yesterday. But this one, since it's curved, but how exactly up to the left? Well, here's where the law of reflection kicks in. So I'm going to draw a normal line from that point back to the center of the circle. Okay, see this this dashed normal line, and this angle of incidence, let's say it's like 29 degrees, has to match this angle of reflection, which would also be like 29 degrees. Just make up the number, but you guys get the idea. The points like that. Okay. Now, if you extrapolate that back, it's always going to cross through a point that I'm going to call the focal point, which happens to be half of the distance to the center of the circle. Right? So we'll formula right here. Focal distance, this F focal distance is half of the radius of the circle. Right, so that's probably the last time you guys are going to see that, because for the rest of these, I don't really care about the circle anymore. All I care about is this focal point, because all the lines are going to go through there. Take another ray, say once top of his head straight towards that focal point, it's going to boing, bounce off parallel to the ground, extrapolate backwards, and you get the image. Now this is like looking backside of a spoon. The second picture is also like looking backside of a spoon. In fact, if you guys went home and tried this out, looking backside of a spoon, you're always going to see the same thing. You're always going to see an image of yourself that's right side up and smaller than yourself. It'll be called virtual image because it's on the other side. This last one approximates a plane mirror. It has a slight curve to it, but not very much. And the fact that it approximates a plane mirror, the image is pretty close to equidistant from the object, from the surface compared to the object on the other side. And it's also get pretty close to the same height. Right? A true plane mirror, the focal distance would be infinity, being infinitely far away. Okay. All right, so that's going to bring us to concave. What if we turn this whole thing around? So instead of convex, what if I take this mirror, go that way with it? Let's do this. I'm going to start with a pretty shallow type mirror. Let's get this kind of to the left too. Okay. Kind of shallow type mirror. Okay. That has a focal length that's like way off, say like over here, or focal point, I should say. Here's the focal distance. Okay. Like then we're going to have a more tightly curved mirror, more tightly curved mirror. We'll just get more tightly curved mirrors for some version of this. So I'm going to move the focal point to here, and then we'll go like right about here, and then finally we'll put it like real close to the mirror surface, something like that. Okay. Okay, so like the focal point is either getting closer, which there's one of two different interpretations going from top to bottom. Either start with a pretty flat-ish mirror and it's getting more and more tightly curved, right? Or if you like, you could say that you're going to have an object that starts pretty close to the surface, which the top picture could approximate, and you're just pulling the that curved surface further away, so that, see if I put an object like here, 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 here. Right. Same idea as like just pulling the mirror further and further away from you, like away from your face. Right. There was just a couple of things I was passing around last class. Does anybody see? I'm looking for a cosmetic mirror. Do you guys see like a handheld mirror? See something like that? Okay. Or now we're there. Thank you. Okay. I'm also looking for this fine saucer right here too. Yeah, thanks so much. I'll pass these around for you guys too, but just want to introduce those and tell you what the application is. Right, so let's do ray diagrams. Find my, where's my pink pen? Oh, here it is. So same method as yesterday, but it's going to be a different outcome. So remember, there's like a billion rays of light going all different directions. So we only have to follow a couple of rays to figure out where the image is going to be. Where's the reflection? One of these we're going to go skirt the top of his head parallel to the ground. Okay. Now that one's going to bounce off through the focal point. This time the ray light actually will go through the focal point because it's on the same side as the reflecting surface, right? Just like that. Okay. Now this one though, extrapolate backwards. I mean, we did a lot of extrapolation yesterday, so same idea, right? I'm going to extrapolate backwards and take this as far as I can up to the right, because you guys will see why in a moment. Okay. Like this. Okay. Then I'm going to take another ray light, go top of his head, connect to the focal point. Take that all the way back to the mirrored surface, right about there. Okay. And then that's going to bounce off back parallel to the ground again, which is about like that. And then same story is extrapolate to the right. So extrapolate to the right. Okay. Oh, actually, this converged. A lot of these examples I've been doing, they've been like skirting like the edge of the paper, but this one worked out pretty well. So put this right here. Okay. And this would be your image. Okay. So here's the object. Here's the image. Okay. And what kind of image are we talking about? Well, it would be a virtual image because it's on the opposite side. I mean, same stories. Yesterday, they were all virtual images also, right? The reflection looked like it was on the opposite side. I don't know how reflection works out. And it would also be upright because he's standing upright. But that was also the story yesterday. They were all upright virtual images. Right, so, okay, they're all upright virtual images, right? Well, not so fast, because these next images are all going to be different. Every single one of these is going to be a unique scenario. Okay. So let's bring in this mirror right here. Okay. Now this handheld mirror, on one side it's just a flat plane, but on the other side it's got a slight concave curve to it. And you see the advantage of having a mirror like that. This is a cosmetic mirror. See what it's going to do is it's going to blow. Say you have your face nearby. It's going to blow up your face real big so you can get a better image of yourself. Okay. Now, for this to work out exactly, replace the stick figure like with your eyeball, like your eye is like looking at this mirrored surface. Your eye has to be inside the focal length. Okay. See, these other ones, it looks like your eyeball would be outside this focal distance, outside this focal length. I wonder how these are going to turn out. We're going to find out. But if it's inside, then the reflection should be really large. So I'm going to pass this mirror around. You guys can try that. Should work. But if you back up the mirror too far, well, we're about to find out what's going to happen. So what if you positioned your eye right on top of the focal point? What's going to happen? Something really weird. You guys can see it in real time too. It's that mirror's being passed around. So let's do the same method we've been doing. Got ray of light, skirt top of his head parallel to the ground. Let's kind of bounce off, going straight through the focal point. So far it's all good. Okay. But remember what we've been doing yesterday and what we just did for the next ray light? We went from the top of his head, connect that to the focal point. Here's where it all blows up because I need that to go all the way to the to the mirror surface, but it's never going to do that because it's pretty well vertical, isn't it? So now what? I can't really make sense of this Ray diagram. And actually, that's all right, because the answer is that there would be no image at all. No image is the answer to that one. So as you guys pass around that cosmetic mirror, if you back it up right to the point where your eye is sitting right on top of the focal point, I can tell you what you'll see. You can confirm this too, scientifically, is that you're going to see a giant blur of light that's not really a discernible image. Okay, so what if you back it up even more so that your eye is outside this focal distance? Okay, well, let's say it's like barely outside, right? Like somewhere between F and 2F. 2F might be about that here. Okay. What's this going to do? Use our ray diagram method. So one ray of light parallel to the ground. That's going to bounce off to this focal point. Okay. Then another ray of light, top of its head through the focal point. That's going to bounce off back parallel to the ground. And where these two cross, that's going to be your image. Now this is the first time on this paper that you've seen something like this, where it looks like the image is actually hovering in front of the mirror. It's on the same side as the object, isn't it? Okay. This is called, well, it's inverted because it's upside down, inverted, okay. But it's called a real image. It's an inverted real image. Okay. Now, I wish I'd drawn this guy a little bit closer to the focal point, but you can kind of see this effect. See how the image is kind of behind the, actually, let me dig up some from last class. There we go. Because I did last class. I want you guys to sort of see it, right? So if I have them a bit closer to the focal point, I should have done this. Okay. See how the image like shows up back here? Okay. Actually, that one's really wonky. Here's a real good shot right here. So it's the same idea, right? The image shows up right here. Now, what does that mean if the image is like behind the object? Well, the way you would see it is you'd have to have some kind of screen, right? Like a piece of paper or screen. And you guys see this eyeball, like you're looking this way. So you could see it that way. Now, of course, it would be upside down, it'd be inverted, but you'd be able to see an image projected like that. They had like a big light source behind the object, like that. Okay. Now, what about if you back up even more to like more than twice the focal distance away, more than twice the focal length away. Okay? So same method we've been doing, ray of light parallel to the ground, and bounce off the surface through the focal point, straight down. Okay? Then from the top of his head through the focal point, and it's going to bounce off back parallel to the ground. And yeah, those two lines will cross right there. Right? This is also an inverted real image. Inverted because upside down, and real because it looks like it's hovering in front of that mirrored surface. Okay? And you know what? This is a really good explanation for something that sure a lot of you guys have seen by now. You guys seen this flying saucer looking deal with the pig inside? Throwing a couple of guitar picks. And so gonna try to get this to work on both video and in person. But you guys see, hey, a couple of parabolic mirrors, right? So it pulls apart, and they're concave parabolic mirrors. Put this together, and this is a really good illusion. So first for the video, if you're watching this video, then this definitely works. For all the video watchers, there's the plastic pig right there. Notice the pig is facing towards the right, but I put the lid on, and now it's facing towards the left, right? Hey, it inverted, switch directions. And then you guys in class, doesn't work super well. I can only tip this so far, but kind of see an image of a pig starting to pop up right there. Okay. There it is. Ooh, actually, that's pretty good. You guys see that? Okay. So I'll pass this around so get a better picture. But it's a really good illusion. Like the pig looks like it's hovering right there. Like you want to grab it, but it's not really there. It's one of these guys going on. Okay. Watch. You guys good with this? Now, this is a ray diagram. I thought like a ray diagrams. This is a graphical method to figure out where the reflection is going to be. But there is an equation that you can use too. So the equation goes like this: 1 over the focal length, focal length, is equal to 1 over distance of the object from the mirrored surface plus 1 over distance of the image to the mirrored surface. So supposedly this should line up with these ray diagrams. We're going to test this out. Here's what this looks like in variable form. 1 over f for focal length equals 1 over do plus 1 over di. So I'm going to pick a few of these and we're going to see how close these are. Wait, is this? Yeah, we start with let's say this guy right here. I haven't tested this out ahead of time. We're going to see in real time. Does this match this? Okay. So I'm going to measure in centimeters. What is the focal distance? Okay. Now this looks like 8.2, maybe 8.2 centimeters from here to here. It's focal distance. Okay. Oh, also when I start plugging in numbers, you guys see how the focal distance, focal length is on one side and the object is on the other side, right? The way you'll handle that mathematically is somebody has to be negative and somebody has to be positive. Okay. So I'm going to define the object as being on the positive side. I know it's kind of reverse number line, so positive to left, negative to the right. So I'm actually going to call this number negative 8.2 centimeters. So plug in 8.2 centimeters for f. 1 over negative 8.2 centimeters equals 1 over distance of object. I'll treat that as an immeasurable value 2. How far is the object from the mirrored surface? This looks like, pretty well exactly 6 centimeters. I see 6 centimeters. Okay. So I'll call this 6.0 centimeters, and this is positive, because from objects on the positive side. Let me see what the calculation says where the image should be. Okay. And I hope it's about here. Let's do a little sneak preview. About 3.5 to 4 centimeters on the negative side, 3.5 to 4. All right, let's see how close. So subtract over 1 over 6. So that's 1 over negative 8.2 centimeters minus 1 over 6.0 centimeters. Right, that fraction minus that fraction is equal to 1 over di. Just follow through some algebra steps. Okay. What is that? What is 1 over negative 8.2 minus 1 on 6? That's negative 0.2886, and that'd be 1 over centimeters is equal to 1 over di. Some of the later calculations, I'm not going to do all these middle algebra steps, but you guys see, right? I'm going to subtract this over. Okay. And then the last step is to do the reciprocal of both sides. So if we take reciprocal, I can say distance image is, I have a reciprocal key right here, okay, above the 7 key. You have this model calculator. So all right, negative 3.46, and the unit would be centimeters. Okay, so pretty much 3.5 centimeters on the side of the focal point. Okay. And what was it again? Looking at right here. Yeah, this is my measured value is about negative 3.7. The algebra says it should have been about negative 3.5, if we round it a little bit here. So yeah, pretty much that's exactly where the reflection shows up. Let's do it for a plane mirror, which the closest one I have here is this picture. And Paul Hewitt yesterday with his candle did a ray diagram for a plane mirror. This is a plane mirror. This is pretty close to that. So 1 over focal length is equal to 1 over distance object plus 1 over distance image. Okay. Let's try for this. Now, if you had a true plane, okay, you guys ready to think critically? Got a good critical thinking question for you guys. What would be the focal length for a true plane mirror? You can figure out the answer to that question. How far away would focal point be for a plane? How about this? Let's go back to this circle I said I wasn't going to bring it up again. Circle, right? That fits flush to this parabola. Okay? If you have a true plane that's flat, wouldn't the circle have to be infinitely big? So wouldn't it have an infinite size radius? Divide by 2, wouldn't the focal point also be infinitely far off to the right? So mathematically, for a plane mirror, I'm going to treat, let's say f for a plane mirror would be infinitely far away, infinite number of meters. I guess meters would be the unit, right? Let's plug that in. What's 1 over infinity meters equals 1 over distance object I'll use this picture to approximate this because it looks pretty close to the story. This guy is sitting about 4 centimeters from the surface. Let's go 4.0 centimeters plus 1 over distance image. Okay, so you're solving this, right? Okay, next critical thinking question. I bet some of you guys are going to get this next question right. What is 1 over infinity? What's that equal to? And it's not infinity, it's what's 1 divided by infinity? How about this? Say someday you go buy a lottery ticket, okay? And there's say like a 1 in 20 million chance of winning the jackpot. 1 in 20 million. Okay, so for all practical purposes, your chances of winning the lottery are pretty well what? 0. 1 in. Here, show it to you guys. What's 1 over 20,000 million? 1 over 20 million. That's a tiny, tiny, tiny decimal. Okay, so the bigger you blow up the denominator, doesn't this pretty well approach 0? Okay, that's a good tidbit to know. 1 over infinity is equal to 0. And if you guys ever take a calculus class, you guys will see that come back too for infinitesimals. Okay, but 1 over 4 centimeters plus 1 over distance image. Okay. Now, you could go through the algebra, subtract over 1 over 4, take the reciprocal, or if you guys like, at a glance, can you guys see the only number I can fit in here to balance this equation and zero it out? What does distance image have to be? Like -4 centimeters? Wouldn't that be true? Plug in -4 here, 1 over 4 minus 1 over 4, that would zero out. Okay. All right, so I hope this image is about 4 centimeters over on the other side. Let's see how close. Yeah, that's pretty well 4 centimeters, isn't it? I'm reading like 4.5, but pretty close to 4. Okay. Oh, but I mean, if we're talking about a plane mirror, your image, of course, would be on exactly the opposite side from you. Okay. Let's try one of these concave examples. Okay. Now remember, every single one of these scenarios worked out differently, so that was unique. Maybe I'll pick this top one just because you guys have some, you guys have a cosmetic mirror being passed around, so let's check this one out. Check what this is. So, wallpaper. 1 over focal length equals 1 over distance object plus 1 over distance image. Say we solve for distance image, just like we've been doing all along. So focal length, see exactly what it is on this paper. So from the surface to the focal point, I'm reading 9.1 maybe? Yeah, let's call it 9.1. 1 over 9.1 centimeters equals 1 over, now object. I'm gonna go 3.5, yeah, 3.5, let's call it 3.5 centimeters plus 1 over distance image. Notice I have all positive numbers so far, because they're both on the same side, they're both on the side of the object. So positive focal distance also corresponds to a concave mirror specifically. Like that. So I'm going to subtract over 1 over 3.5. So what is 1 over 9.1 minus 1 over 3.5? So that difference comes out to be -0.1758, that'd be 1 over centimeters, plus 1 over di. Take the reciprocal of both sides, reciprocal. So invert 1 over that. Distance image is -5.7 centimeters, well, 5.6875, not to that, 5.7 centimeters. And it should be on the opposite side because negative. Let's see how close we got it. Okay, so from the surface, okay, my image is looking about 3.5 centimeters, that's right, from here to here. So -3.5, and the math said it should have been about -5 point something. Okay, so close enough, I guess. This is kind of in the ballpark. Okay. Mathematically, you should have been probably right about here. Okay. That's really close. Okay. You guys agree with that? Okay. Then application of this stuff for you guys. Yeah. Like flip my screen over, share screen 2. How many of you guys have ever seen something like this, like a pair of giant dishes facing toward each other? You guys ever seen this? Maybe yes, maybe no. You might see this possibly outside a science museum would be a good place to see it. Actually, I do know where a specific pair of these is if you guys ever happen to be in Gainesville at the University of Florida and you find the physics building, in the lobby of the physics building, there's a bunch of cool physics demos, including a pair of these parabolic dishes. Parabolic concave dishes. Okay. Now, these will reflect sound. Sometimes these are called acoustic mirrors. Okay? So they'll reflect sound, but in a really special way. Okay? So here's a bunch of other pictures. Each of these is going to have a focal point, just like you guys saw with the ray diagrams with light. Okay? And these are called whispering dishes. That's what I Googled to get these pictures. Whispering dishes, because if you whisper, whisper a conversation at the focal point of one of these dishes, where maybe somebody just a couple meters away shouldn't really be able to hear you, well, that sound's going to get concentrated and reflected across the field or across the lobby to the other dish. And if you have a friend with you who has their ear at the other focal point of the other dish, they'll be able to hear everything you're saying. Yeah, so if you ever see a pair of dishes like this and you're with a friend, try that out, because yeah, it's really weird. You can hear everything you're saying. And fun application of that is actually something called a whispering gallery. Now, a lot of these are just built completely by mistake, but there's some rooms that are like either like elliptical shape or circular shape that create natural like whispering dishes sort of by accident. So if you're standing one special place in the room, you can hear a conversation that somebody's having somewhere else. Wikipedia actually has a whole list of whispering galleries. And funny thing too is some of these are actually legislative buildings. So yeah, I remember reading a story about some of these too. It's like so there'd be like legislators that would. Did you guys see like a capital? Like United States Capitol. Oh, I didn't realize that. Yeah. So yeah. So sometimes legislators will like spy in on their colleagues and hear some conversations that maybe should be because they're whispering gallery. All right. So that's pretty fun. Look back over. Let's not go out these questions for chapter 17. There's some formulas here, so thanks to these formulas first. Okay. So the first formula says angle of reflection is equal to angle of incidence. So that is the law of reflection. Okay. The couple of formulas next to it. Distance image is equal to negative distance object. So now this is only true for a plane mirror, that the image would show up exactly on the opposite side of the mirror. If you have a parabolic mirror, then this equation doesn't apply, only for a plane mirror. And same story for the next one. So height of the image is equal to height of the object. That's true for a plane mirror. Both of these are only true for a flat mirror. Okay. Now this one down here, well, we've just been applying this. Right? 1 over focal distance equals 1 over distance object plus 1 over distance image. Okay. Distance image or distance object. So this will work for both flat mirrors, but also parabolic mirrors. Okay? And this last equation says M stands for magnification. Magnification is defined as, see that like the triple line, looks kind of like an equal sign, but has 3 lines. That means is defined as. Magnification is defined as height of the image compared to height of the object, okay? Which turns out to also be the ratio distance image over distance object, if you take the absolute value. So that's the basic trigonometry relationship. So what this is saying is how much is something magnified? Well, you guys are passing around the cosmetic mirror right now. So if you compare the height of this reflection compared to the height of the object, just take the ratio of those. That's what magnification would be, wouldn't it? It's defined as that. Number 54. A ray of light strikes a mirror at an angle of 53 degrees to the normal. So you need a normal. Remember, you need a normal line to measure your angles with respect to. What is the angle of reflection? So start with that. Angle of reflection. 54. Zoom out here. 54. Okay. So I'm going to draw a vertical mirror. So there's my vertical mirror. I need to draw a normal line for a reference. Remember, normal means perpendicular. So I draw a perpendicular line. Okay. You guys see that? Okay. And then a ray at 53 degrees. I got a protractor. I'm actually going to measure out 53 degrees. Pretty good practice, right? There's 53. So here's your incident ray. This right here is a 53 degree angle. okay, and that's equal to theta sub I, incident angle. Okay, and well, wall of reflection says it has to bounce off also at 53 degrees. So I just zeroed out the normal line. I'm gonna sweep out 53 degrees. That's right here. This angle of reflection must also be 53 degrees, just like that. Also, here's a part B. Part B says, what is the angle between those two rays, the incident ray and the reflected ray? So that one's just talking about this full angle right here. Like that. Maybe I'll call that angle beta. And beta, of course, would be 53 plus 53, which is 106 degrees. Okay. Guys, good? Next question. Jeweler's mirror. A jeweler inspects a watch with a diameter of 3 centimeters by placing it 8 centimeters in front of a concave mirror that has a 12 centimeter focal length. Where will the image of the watch appear, and what will the diameter of the image be? Right, so how big is the watch get blown up? Right. Now, we already did a ray diagram that pretty closely models what that question is asking. So you guys can figure out which one. So notice that there's a 12 centimeter focal length. Let me start with this, concave. Right, so concave, so between the 4 that we did today versus the 3 yesterday. Okay. Well, it's going to be one of the ones that we did today because those are concave. So one of these. Okay. There's a 12 centimeter focal length, but the object is 8 centimeters from the surface. So you guys see that the watch would be inside that focal distance. Okay. And the only picture that aligns with that is which one of these? Yeah, the first one, right? Where the object is inside that focal length. Okay. Oh, which is exactly what you'd want anyway. I mean, that's the whole point of this kind of mirror, right? Is to blow up the image and make it really big. Okay. So let's do a ray diagram for this, and then we'll apply this equation and see how close it lands. So 50, or sorry, no, 71, number 71, jeweler's mirror. Just use a whole page for this. So I'm going to dash off a reference line. Okay. I'm actually going to mark out these two. So it's going to be 10 centimeters, 11, 12. Okay. So I'm going to put my mirror right here. Okay. Make it a concave mirror. Okay. The watch was 8 centimeters, or remember, mark the focal length. So 10, 11, 12. Okay. There's a 12 centimeter focal length. Here's the focal point. I make this all fancy, mark out focal distance equals 12 centimeters. The watch was located at the 8 centimeter mark. So that's right here. So distance object is equal to 8 centimeters. Okay. And it said it was 3 centimeters tall. So 3 centimeters, this tall right here. This, you got like a watch face. And put some hands on this watch. I get read 10, 10. You guys ever notice that? If you go look, a lot of advertisements for watches and clocks, they're pretty much universally reading 10, 10. Do you guys ever see that? You guys know why? Why they always read 10, 10? So it has to do with advertising originally. So let's say you go back probably 100 something years ago. Say you had different watchmakers and they're trying to make their watches more appealing in the ads. They said, oh, well, let's maybe have some kind of symmetry for the hands, right? Because if it's asymmetrical, then that doesn't appear. One of the theories of what makes something aesthetically appealing has to do with symmetry. So they started making the hands read it like 820 was a pretty common one, to go like 820. But the problem with 820 is it looks kind of like a frowny face. But if you turn that upside down to 10, 10, it's more like a smiley face. So it has like a positive connotation. Well, I don't know. I read that on the internet, so it's probably true. So learn at school. Griffin's Reddit plus. So let's do ray diagrams, just like we've been doing. So we'll have one ray parallel to the ground that's gonna boing, bounce off to the focal point. Now, we did one of these earlier, so let's extrapolate back up to the right. Okay. And then we'll go from the focal point through the top of the watch. Ooh, man. Well, if I extend my mirror, it's gonna extend kind of up here, right? I do that. Go kind of a shallow curve. So kind of like this. And then that's going to bounce back parallel to the ground, that particular ray, which is approximately parallel to the ground. Let's extrapolate back to the right. Ooh, this might barely fit on the paper. Is it gonna fit on the paper? Oh, it just goes to the edge of the paper. Woo! That fits right in there. And they just, what if they did on purpose? They probably tested those numbers out, anticipating. Some physics teacher that's barely fits out on the paper. These are book numbers, right? And so, got a watch face should show up right here. Something like this. Okay, just right at the edge there. All right. So, where is that? We got a measurement. So from pretty well the edge of the paper. 10 centimeters, about, I'm looking at like 14 and a half or so, about 14 to 15 centimeters should be the distance image to that surface. You get about, call it D sub I. Okay. Let's start with this. 14.5 centimeters is my measurement. That's negative because it's on the opposite side. Well, let's run the equation and see what it should have been. Hopefully it's kind of close to that. I forget what it is, but we're gonna see. So 1 over distance, or sorry, no, 1 over the focal length is equal to 1 over distance object plus 1 over distance image. Okay. Focal length was given as 12 centimeters. The object was 8 centimeters. Those are both positive numbers because they're on the same side. And distance image. So this has to come out to be a negative number. I hope it's pretty close to this, but we're going to find out. Okay. So let's do the algebra steps on the calculator. So I'm just going to start with 1 over 12. I'm going to subtract over 1 over 8. Okay. Now that's going to be equal to 1 over di. So the last algebra step is to take the reciprocal, right? 1 over that. And that is, I showed you guys this subset more thoroughly earlier. Negative 24 centimeters. Okay, so ray diagram says that, the math says it should have been negative 24 centimeters. Okay, right order of magnitude, I guess. Okay. So yeah, I guess that's the least accurate ray diagram we've gotten so far, but that's all right. There's a follow-up question that says, what would be the diameter of the image? Okay. Let's play off the equation. I trust the equation more than my ray diagram that has curvy lines and all kind of crazy. So let's play off the 24 centimeters on the opposite side. Okay. And let's remember, height of the image compared to height of the object is equal to the ratio of the distances, distance image over distance object. Negative, because it could be a couple negatives they're going to cancel. So we're solving for how big is the watch going to be? How big is it blown up to? Okay. The object itself had a 3 centimeter diameter. And so negative, the image should have been at negative 24 centimeters. And the object, remember, was over here at 8 centimeters. The two negatives cancel. And you guys see how this is a 3-to-1 ratio? 24 over 8, that's 3-to-1. Okay, so it gets blown up by a factor of 3. Cross multiply up 3 centimeters. 3 centimeters times a factor of 3. Height of the image should be 3 times 3. And here I'll write it up. 3 times 3 centimeters. Should have been 9 centimeters. Should have been 9 centimeters tall. Okay. So the watch just got blown up by a factor of 3. That's why this jeweler can work on this watch. I wonder what my ray diagram said about that. Huh. Find out here. So, oh, actually, it's pretty close. It's showing 8, like 8.0. Huh, that's interesting. So the height actually worked out pretty close on the ray diagram. Reading 8 should have been 9. Number 64. Describe this image. Is it going to be virtual, inverted, upright, smaller, or larger than the object? So they're representing the object as an arrow. And you usually either see candlestick figures or arrows. They went with arrows. And see how it's halfway between the focal point and the center of the circle? Maybe there's something special about that. No, see. Let's go ahead and solve this one with the equation. Wait, do we have a ray diagram that's kind of close to that, kind of models that? Maybe this is sort of close. Oh, you know what? I know what that is. That's actually really close to this picture, isn't it? Okay, remember where the image gets projected behind the object? Right? It should be really close to this. Let's see how closely that matches with the equation. So this is number 64. We're going to go 1 over f equals 1 over do plus 1 over di. We're interested in image. I could do this. I could break out my ruler and start measuring these and get numbers, but I kind of like that they just left it blank so that, let's solve this in terms of proportions. So whatever this f is, the actual object distance would be 1.5 times that, right? So maybe I'll do like 1 over, there, it's too crazy. Let's go 1 over 1 compared to 1 over 1.5. Like it's gonna be a ratio, it's gonna be that ratio, right? I haven't solved it this way today, but maybe it's a little bit different perspective, right? That's a good reason to solve these problems like this. Get a little bit different perspectives on these. We kind of have an idea what the answer should be anyway. What's 1 over 1 minus 1 over 1.5? And of course, take the reciprocal. So here, 0.333 is equal to 1 over di. If you take the reciprocal of that, distance image should be 3. Well, three times the, should have done that. I guess a factor of 3, right? 3 times, factor of 3 times the original focal length, right? Video, f. Okay, that's what I come out to. Right, so yeah, I could believe that, right? Because whenever this focal distance is, multiply a factor of 3 to get back to here. That looks about right. I can believe that. Again, you could break out a ruler, get some actual measurements, and should be consistent with that. Okay. How about this one? We got another concave mirror. This is concave. This is concave. Find the image position and height. Oh, crap! I get the height of these things. That's all right. Got a little time left. Okay. Now this one is almost double the distance from the focal length, and they gave you some numbers. Huh. Hey, that's kind of like this picture. Remember, actually, should line up pretty close to exactly this picture because this guy's almost twice the focal distance away. And you see where the image is going to be. About the same spot. Pretty close to. Okay. So let's run the numbers. 1 over focal distance of 16 centimeters equals 1 over distance object of 31 centimeters. Plus 1 over distance image or solvent for. Okay. Subtract over, what's 1 over 16 minus 1 over 31. Then reciprocal, distance image should be 33.1 centimeters. Yeah, that is in line with the ray diagram, right? So it's approximately the same position as the object, just a little bit behind it. That's exactly what that says. And if you want to do hi over ho equals di over do, let's do that real fast. Should be an inverted real image. Oh, negative. So let's figure out what this is. So the original object was 3.8 centimeters. The image was at this location. That feeds in right there. Positive 33.1 centimeters. The object was at positive 31 centimeters. So it's expanded a little bit, magnified a little bit, but hardly anything. So what's 33.1 over 31? It's magnified by about 6 or 7%. Multiplied by 3.8 centimeters. Height image is negative 4.06 centimeters. Negative means inverted. Okay, last one, real fast. Draw the ray diagram to determine the height and location of the image. So number 75. The ray diagram.
Interruption, teacher. Also, girls lacrosse practice is Vieira Regional today. Girls lacrosse practice is at Vieira Regional today. Thank you.
All right, so we're going 4 centimeters to the right. Let's go ahead and use the numbers, point, point by point. There's the focal point. We got a convex mirror like the ones we did yesterday. And the object is 8 centimeters the opposite direction. That's point right there. There's the object. So quick ray diagram, figure out where the image is going to be and what it's going to look like. So, oh, this is looking backside of a spoon. Remember, there's only one possibility for what happens looking backside of a spoon. The image is always going to be upright and virtual. And that's exactly what this shows. Here it is right here. Here's the image, and it's upright and it's virtual. Right, go home tonight, try this out, pull a spoon out of the cupboard, look backside of it, and that's what you will see. Okay, who's got any questions? All right, so yeah, I didn't get to start on reflection today, or sorry, refraction, but tomorrow we'll break out this guy, we'll do some Snell's law. So stay tuned. Yeah, you guys have a good afternoon.